Hello, welcome, and I'm just going to pass it off to Jim, who's going to introduce our speaker today, Chris. And so, Jim, do you want to take it away?
Hi, thanks, Laura. I have the privilege today of introducing our guest speaker, Chris Magwood. You're in for a real treat. Chris is from the Endeavour Centre in Peterborough, Ontario, and he's going to talk about the carbon elephant in the room. That's his expression, not mine, but I think it's a really good one. Chris says he's really obsessed with working on better buildings for people on the planet. Zero net energy, zero carbon, zero toxins, and zero waste buildings. And I think that's a pretty substantial goal to work on those things. And any of you who've been around for a while and were involved in the Straw Bale building, you'll know that Chris is the author of that famous book. If you talk to anybody about Straw Bale building, they'll say, yeah, Chris Magwood wrote that book. It's a good one. So anyway, I'll turn it over to Chris, and he's going to talk about carbon counting is the right word? Not quite, I don't think.
Sure.
Go ahead, Chris.
Okay, thanks so much. Thanks everybody for taking your precious lunchtime to spend with us here. I really appreciate people taking the time to think about these things in their spare moments. I know a lot of us don't have very many of those spare moments, so thanks for sharing that with me. Today I'm going to talk about buildings as a potential carbon sink. So a way to think about building and actually achieve buildings that go beyond doing less harm and could potentially be part of a larger and more comprehensive climate solution, but looking at what the building sector in particular can do to achieve that. Yes, like Jim said, I work at the Endeavour Centre, which is a sustainable building school here in Peterborough. About a year ago, we started a sort of sub-project called Builders for Climate Action, which is starting to kind of build a life of its own. At the end of this presentation, I'll show you the material emissions calculator that we're just about ready to launch publicly. And we've produced some white papers and some studies. And so over the past year, the carbon focus has really become central to my work, and it's really great to see it sort of rippling through the building world it's quite surprisingly quickly. And as an acknowledgement of my own, I'm the father of a outspoken and vibrant 26-year-old woman, and she tells me things like these two remarkable young women are telling the whole world, which is it's up to the generation that sort of has their hands on the levers right now to do the right thing and to not dawdle around and not waste time, and to make trying to fix the climate the central part of our work. And so I'm definitely working to do that myself, and hoping to inspire other people to do the same. And for those of us in the building sector, we are responsible for a pretty big chunk of this climate problem. If you look at fuel emissions by sector globally, the building sector is of all of those emissions, and slightly more than half of that from building operates. And that side of the equation has been receiving more and more attention over the last couple. Hopefully I'm back and back for good. So I think I left off saying, that we've been doing a good job of focusing on these operations. A key focus of the work, but it's only very, very recently that any attention has really been paid to the emissions that come from the materials that we use to make those buildings in the first place. And the first sort of look at that people did, they saw that key core and shell materials, which is basically concrete and steel, for the building sector, were about 11% of total fossil fuel emissions on the planet. But then a sort of more recent scan looking at materials other than those big ones shows that there's about another 10% of material manufacturing emissions related to buildings. So, you know, in total, that's 20% of global emissions. And so this is a piece of this puzzle that we really have to pay attention to. And it's really important because these are emissions that are happening right now. Like when we bring a building into being, the emissions associated with its materials have sort of occurred in the, you know, relatively short time frame prior to us building that building. And that means there's no chance to address them later. So, you know, with energy efficiency and operational emissions, we can always clean up our energy source. We can always improve the building, but the emissions from materials, they've gone to the atmosphere, and there's sort of no calling them back or doing a better job once we've committed to those. So I'm going to be focusing specifically on material emissions, looking at the product phase of life cycle emissions. So if you're familiar with LCA, this is stages A1 to A3 in a life cycle assessment, or better known as cradle to gate emissions. So this is looking at everything that goes to the atmosphere as a greenhouse gas, from harvesting or extracting raw materials to transportation to factories, and then all the processing that happens in that factory. So it's everything it takes to get a product from raw materials to a ready to install product. So it's not including transportation to the job site, or any construction emissions or end of life emissions. But the reason that I'm putting the emphasis here is that these emissions are typically, 60 is a low number. It's more often 70 to 80% of the full life cycle emissions for any building material are here at this product phase. And so, you know, this is really the lion's share of this problem. And it's also the part of the issue that we can actually address by thinking about the materials we're using and potentially material swapping. So that's a little bit about the background, what piece of this puzzle that I'm actually looking at today. And I'm going to be talking about not only materials that create emissions, but I'm going to be talking about materials that are carbon sinks or offer carbon storage in buildings. And essentially what I'm talking about here is plant-based materials, or I might use the term biogenic materials. And they're very, very different than non-biogenic materials, because plant-based building materials, whether it's a tree, or as Jim mentioned, a straw that goes into a straw bale, or a piece of bamboo, or a slab of cork, or hemp, or and timbers of all different kinds. There are so many plant-based building materials out there, and all of them draw carbon dioxide out of the atmosphere to grow themselves. So through photosynthesis, that CO2 comes out of the atmosphere, and the carbon atoms stay in the plant. And most plant material, dry plant material, is about 40 to 50% carbon by weight, and all of that carbon came out of the atmosphere while that plant was growing. In order to transform those building materials, or to transform those plants into building materials, we will create some emissions through harvesting and manufacturing. But in all of the examples I've looked at, those emissions are much smaller than the drawdown that happened when the plant was growing. And so what that means is there's a whole category of materials that offer net carbon storage. So as I'm doing the carbon accounting, and I'll show you what that looks like shortly, but as I'm doing that accounting, essentially any materials that have emissions associated with their production are a positive number, you know, kind of drive the carbon footprint of the building up. And then these biogenic materials are negative numbers in that accounting, and they're drawing that total down. And so, you know, you can right away kind of sense that having a bunch of negative numbers in your accounting is going to mean that it's possible to achieve a much lower carbon footprint than we would otherwise be able to. And I'm going to just sort of show you a quick graph here that visually tries to explain that in a bit more detail. So if you think of the center line of that graph as, you know, a static emissions at the moment, when we're looking at plant-based materials, there's usually a small burst of emissions associated with planting those materials in the first place. So whether that's reforestation or agricultural practices, there will be some emissions associated with that. But then over the lifetime of that plant growing, and our time scale here we don't actually have a scale, because this could be, this period of photosynthetic drawdown could be 3 months for a wheat straw, or it could be 80 years for a northern species tree. So whatever time it takes for that plant to grow and mature, it's pulling CO2 out of the atmosphere that whole time. So in effect, there's less CO2 in the atmosphere when that plant is done growing than there was when it started growing, besides the fact that humans keep adding more to the atmosphere. But you can see what I mean. And then, like I was explaining, through harvesting, manufacturing, transportation, and construction, we are going to be adding emissions back into the atmosphere. But as long as those emissions are less than the amount of CO2 that the plant has drawn down, that means that over the lifespan of the building, which, you know, we would certainly expect all of our buildings to last at least as long as the next few decades, when we're really, you know, having to scramble to try to fix the amount of carbon dioxide in the atmosphere. These building materials, these plant-based building materials, are literally acting as carbon sinks or carbon banks or carbon stores. People use a lot of terms for it through the length of time that building exists. And obviously, the longer we can make those buildings exist, the better and more meaningful that storage becomes in the overall kind of climate change scenario. And then at the end of life, there's a bunch of scenarios where that carbon can continue being stored. So if we can reuse those materials in another building, then with a small amount of emissions associated with taking them down and retransporting them, that stays in storage. Same with if we're able to recycle them into other long-lasting products that keep the carbon in storage. Potentially, that stuff could be burned in pyrolysis and create biochar. So now the carbon that was in that plant material is literally carbon, and it goes into the soil as a soil amendment. Combined heat and power sources could burn. You could burn that plant material to generate heat and power, and you're obviously returning most of that carbon back to the atmosphere when you do that. If we landfill, it's not the greatest option, but certain landfill practices will ensure that much of that carbon stays locked up for a very long time in the landfill. And of course, worst case scenario, it becomes methane, and we have emissions again at the end of that material's life. So we want to, you know, avoid that if we can, because in all the other scenarios, we can expect the carbon to stay out of the atmosphere, or the majority of it out of the atmosphere, longer than just the building's lifespan. And that maps really differently than any other type of building material. So it doesn't really matter what the material is. If it's not plant-based, its profile kind of looks like this red line, where every single step along the way is an emission. And obviously, the height of that red line, a material with high emissions, it's going to be higher over the zero line. A lower emitting material will be lower. But wherever it falls, it's all emissions. And that means that by the time it gets in a building, you know, those emissions are all in the atmosphere, and they're not coming out from the building. And again, even what happens at the end of lifespan, you know, the emissions are still going to be in the atmosphere. So there's a really different scenario between that red line and that green line that is, I think, a really critical piece of our sector being able to really address climate change and to take advantage of buildings as long-lasting fixtures capable of banking and storing that carbon for decades or even centuries. And so, you know, those emissions, in some ways, this graph is misleading, because that red horizontal line it should actually be an upward curve, because, you know, emissions stay in the atmosphere, and you know, the radiative impact accumulates over time. So if we dump a bunch of emissions into the atmosphere making a building, they drive climate change again next year and the year after and the year after and the year after. So you know, what we really want to do is, you know, get our whole industry down to that zero line or better below it. So I'm going to show you a study that I did that I wrapped up in 2019, where I wanted to look at the carbon footprint of those building materials in some typical residential type buildings. I'm a residential builder, so that's kind of my focus. And so what I did was I picked a really common single family home design, a 2,000 square foot raised bungalow, and a 4-story, 8-unit, 10,000 square foot multi-unit building. And then I gathered what are known as environmental product declarations, or EPDs, which are sort of like report cards on impacts from products, in this case, building products. And what I like about using EPDs as my data source is that the way an EPD is made, the person accumulating the data for an EPD is following a set of ISO standard rules. So there's an international agreement on what you include and what you don't include, and how you actually perform one of these studies. And I also like the fact that in order for an EPD to be kind of released publicly, it needs to be either done by, or at least verified by, an outside third party. So, you know, the companies themselves who are disclosing this information, the data obviously is from them and from their operations, but a disinterested third party has been paid to either do the work or review the work and make sure that the rules have been followed. So, you know, in terms of finding comparable data, this is as good as it's going to get for being able to compare products side by side. And what I noticed as I collected EPDs for building materials was that for every single element of a building, whether I'm looking at foundations or windows or flooring or roofing or insulation, there was always materials that kind of fell across a spectrum of results. And so I've characterized those results with a sort of red typology building. So that in that model, I used materials that were always at the highest end of their category. I used blue to signify materials that were sort of in the mid-range, moderately emitting materials. I used yellow to represent the best materials in their category that are currently available, widely available, code compliant. So I call it sort of best conventional. And then another series of materials that I characterize in green, which just had the best, lowest carbon footprint result, regardless of whether they might be considered alternative or whether it's a material that maybe isn't common in the North American market. That wasn't one of the parameters. It was just, what are the best options? So I'll show you what this looks like when I do all the math. So what I did was, design the building as though it was going to meet Ontario code minimum standards. I'm showing you the results for the 8-unit building here, but the single family building tracks in a very similar way, although per square meter, the smaller buildings tend to have a higher carbon footprint. So then I did material takeoffs, and then I applied the global warming potential factor from the EPDs to the amount of material it would take to meet code minimum standards for that building. And, we don't really dive into, or we won't dive into, all of these materials and details about them. But if I run the numbers for a building with materials that are at the high end of the carbon footprint spectrum, and I think if you scan that list, you'll see this isn't necessarily a weird building or a building that just is an academic exercise in what could a high carbon footprint be. Like, lots of buildings are built with these materials. And in this case, we have over 200 tons of emissions associated just with making the materials to make this building. And that's a really high amount of emissions, and there's literally no way that anybody's going to meet their climate change targets, whether it's locally or provincially or nationally or globally, if every single small building that gets built has a carbon footprint of this kind of size. But this is kind of where we are right now. I then modeled out a building where I just swapped out materials for things that were sort of more moderate emitters in their categories. And what's interesting here is that right away, through some really simple material substitutions, I can bring the carbon footprint of this building down to 68 tons. That's a massive change. That's a huge improvement, and it's improvement made not by doing anything alternative, not by doing anything, out of the ordinary. It's again a very recognizable, suite of materials, but I've more than cut that building's footprint in half by swapping out those materials. Now, my third example building, you'll see that the graph has changed here. I've needed to add a storage direction for this graph to go, because this is the first building that's going to involve some of those plant-based materials. And I think this building actually to me was super exciting. It's not something that I expected to find in this study, but I was really encouraged by the fact that I did. So here's our first negative number. So you can see, instead of going up, the cellulose and the wood fiber board insulation, because of the CO2 stored in them from when the plant was growing, is actually making the bar go down. And depending on the material, the bar kind of goes up, it goes down, depending on what the material is. But at the end of the analysis, this building is responsible for 15 tons of net carbon storage. So the amount of plant-based material in the building is sufficient to offset the emissions from the materials that do have emissions associated with them. And essentially, we've made a zero carbon footprint building on the material side. So if you're setting out to make a zero carbon building on the operation side, this is the flip side of that. You also want to be trying to make a zero carbon building on the material side. And really, the big changes here are cellulose insulation and wood fiberboard insulation, and the best available lowest carbon concrete mix that I could get in my region, and which is pretty widely available. And that's enough to tip a building from being a fairly large emitter to being a zero carbon type building. And then my final example, this sort of maps what we do at the Endeavour Center. So the types of buildings that I'm sort of commonly doing with our programs, where we use a lot of plant-based material. And here, I'm actually able to get that building to store a really significant amount of carbon on a net basis. So here we're storing 117 tons. So, that's storing more than that blue type building was emitting. And so, that's a really pretty remarkable paradigm flip to be able to achieve with a building. And, these materials are not necessarily all common. They're not things that people are using, but they're certainly things that are well within the range of reasonable and practical to be able to move towards and to be able to encourage a greater adoption of. And then the final thing that I did on the carbon footprint side for this study was I modeled that building. So those 4 bars are the ones we were just looking at. I also modeled the building as though it was going to meet Tier 5 of the sort of upcoming National Building Code net zero ready codes. And so the interesting thing that happens here is, if essentially, the only difference between making the building code minimum or more energy efficient is I'm adding insulation and maybe a pane of glass in the to triple pane windows. If I'm adding insulation that has a carbon footprint associated with it, what ends up happening here, you can see, is that we drive up the material carbon footprint of the building in our efforts to try to drive down the operational carbon footprint of the building. And I'm going to add operational carbon into this picture shortly, so you'll see what difference that makes. But it's important to know that one of the impacts of making a building more energy efficient, if you're using those types of insulations, is that you're sort of paying a a greenhouse gas penalty up front in order to do that. But the opposite happens if we're using biogenic-based insulations. So here we're achieving this really great win-win of we're adding more insulation, so the building's going to perform better, have less operational emissions associated with it, and it's storing more carbon up front. So, you know, you're kind of doubling your benefit there instead of paying a penalty, trying to recover that through the benefit of greater energy efficiency. So this is what those buildings look like if I convert the total emissions for the building to a emissions per square meter, which is a sort of better way to express the numbers, because you can then start to compare across building sizes and across building types, and sort of see how they work rather than a gross figure. And again, you can sort of see the reflection there of that wide spectrum. Oh, there should be a minus sign on our 137 over on the far right. But what I want to point out here is that I'm not creating a prescription. I'm not saying that you either build the red building or the blue or the yellow or the green. What I really want to sort of emphasize is that material carbon footprint targets can be just like energy targets. If we think about it, the goals we set out to achieve with our building, you just decide with your client or for yourself, you know, I want to hit a 50 kilogram per meter squared material carbon target. And then you go about designing the building and making the sort of decisions and trade-offs the same way you would if you decided, I want to hit R2000 levels of energy efficiency, or I want to get to passive house, or, you know, I want to, you know, however you set your energy targets, you can similarly go ahead and set a material carbon footprint target and essentially juggle the materials that you want to use until you get that version of that building in the most sort of efficient, effective, affordable way that you can. So that's looking at what the carbon footprint of materials looks like on a single building basis. I then sort of expanded that out, and apologies here for the US numbers, but most of my presentations these days are to American audiences. But the US builds about 240 million square meters of this type of 4-story and lower residential construction a year. And if they keep going business as usual, and so here I'm using an average of the red and the blue type building, on an annual basis, that's 54 million tons of emissions from the materials, from manufacturing materials for residential buildings in the US. And that's 15 coal plants worth of emissions. Whereas if we're able to flip to the carbon storing side, first of all, none of those emissions happen. So, you know, we get rid of those 54 million tons. And then additionally, we store another 36 million tons, or do the equivalent of literally taking out the emissions of 10 coal plants worth of greenhouse gases on an annual basis. And, you know, that's a massive difference. That's a 90 million ton difference between those two options. And I think, you know, we're, as an industry, we're incredibly capable of getting ourselves to the carbon storing side of this diagram in a relatively short time if we really want to. So now I'm going to throw in the operational emissions just so you can see how that sort of adds to the picture. So here's our two graphs again, our 4 building types in code compliant and net zero ready form. And I'm adding natural gas heating for 30 years. So this is mapping 2020 to 2050 in the Toronto, Ontario climate zone. So obviously, if you did this for Winnipeg or somewhere in Manitoba, these numbers would vary, but this is what it looks like in Toronto. And that is that the code compliant building is in whatever form, because the materials aren't changing the efficiency. They're modeled to be exactly the same level of performance. That means there's going to be 10 tons of greenhouse gas emissions from burning that natural gas every year, or 300 tons over the 30 years. And you can see that that's a pretty significant part of the carbon footprint. And in fact, as your material selections get better, the impact of the operational becomes a much bigger piece of the overall puzzle. And interestingly, you know, when we get to the right side here, even though these buildings have the same 300 tons of emissions associated with them, in their operation, because they start at a negative number, by the end of operating this building on the right here with natural gas for 30 years, you can build the building and operate it for less emissions than just building that red type building of the same, size and efficiency. So really important to, to sort of see that the material impact. I think a lot of reasons this hasn't been looked at seriously for a long time is people just assumed that the operational outweighed the materials by such a big amount that it doesn't matter. But when we look at it, especially in the window of the next few decades, where we really are or aren't going to address the climate issue, then the materials are at least as important as the operational. In its net zero form, we've knocked 60 tons of emissions off of these buildings. So 2 tons a year for 30 years, and that's great. That's incredibly important. But if we look at improving our material profiles, then we'll see that any movement, even from the red type building to the blue or the blue to the yellow, et cetera, on down the line, every one of those improvements is a bigger emission reduction than changing the building from code compliant to net zero ready. I tread on thin ice here, and I really want to anybody to think that I'm suggesting that we ignore energy efficiency and only look at materials. I think it's really important to do both, because over here on the far right, we will get the best results for the climate if we're actively thinking about both of these things, where we can use the best materials and the highest degree of energy efficiency to absolutely minimize the footprint of our buildings. The last graph I'm going to show you, and then we'll get away from graphs. Sorry for all the graphs here, but is taking the exact same buildings and now looking at their emissions profile if I heat them with an air source heat pump using the Ontario grid carbon intensity. And it's pretty remarkable how much lower the operational emissions get when we electrify that building. And obviously, this was depending on your grid, you get a very different answer in Quebec than you do in, say, Boston, Massachusetts, where the air source heat pump looks almost like the natural gas. But one of the important things to remember with switching to the electric heat source here is that at least there's the opportunity to reduce the carbon footprint of our electricity grids. Whereas you're going to burn natural gas, you're always going to burn natural gas, and it's always going to have the same amount of emissions associated with it. So here we've dropped the 300 tons to 54 tons on the code compliant version. And what's interesting is the net zero version, we've only dropped it to 48. Like, we've hardly made a difference, because saving operational emissions when you're not making very many, there's not a huge payback for it. And in fact, this is where we see that, we're actually not making back that penalty that we're paying for more insulation, at least not in this first 30 years. Over a longer time frame, you would start to see that reduce. And again, not to be saying that we shouldn't be making these buildings net zero ready, but we just have to make sure that if we're putting a bunch of time and effort and money into making a net zero building, hoping that we're helping the climate, and we're not, you want to know that. Like, you really want to make sure that this is something you're doing intentionally. And ideally, you can see some of these buildings at the net zero ready stage, the yellow and the green type buildings. The yellow one is almost a zero carbon building for the first 30 years, in operation and materials. And the green type building, it's a site of net carbon storage for over a century. So, this is the kind of result where you can say, wow, we actually could, as an industry, make a big impact on climate change if our buildings were doing both of these things, operating efficiently on clean power with carbon storing materials. That's kind of, now this building is actually helping to drive climate change reversal instead of just not impacting climate change quite as much. So the wrap up to this, and what I'd like to sort of have you think about for your own practice, is to think about a carbon use intensity metric that takes both sides of this equation into account. I think it's it's important to remember that that there are two parts to the way buildings impact the climate, and these upfront materials emissions are one part, and then the operational emissions are another part. And if you're not doing the addition there, and if you're just focusing on the operational side, you literally could be having, you know, the wrong kind of impact, even though you're putting all your time and effort into thinking or trying to have the right impact. So, you know, we need to be looking at these two things together, and thinking about that in the as carbon use intensity as a sort of combined metric. I'm just going to do a quick time check here because I know I missed some time while I went offline. Okay, I'll keep going. I'm going to save us some time for questions and answers, but I just want to quickly draw your attention to, you know, the range of materials that are available that are plant-based materials, and this is just a fraction of what's out there and what's coming. Some of these things are materials that we already use or are commonly available. Things like sustainable timber, cellulose insulation, wood fiber board, cork, bamboo, those sorts of products have been around. Waste textiles, hemp type, there's a lot of different ways that hemp can be incorporated into buildings. Straw boards, rice hull boards, there's just such a huge array of materials that are both existing and coming, that, you know, if we can start to both pay attention to these materials, learn how to access them, learn how to use them, start demanding them, start incorporating them into our projects, that's how we will get to those carbon storing results. And I often get the question, so I've folded it into the presentation here, well, are there enough of these plant-based materials? You know, are we gonna have this unintended consequence of encouraging people to build with plant materials and then stripping the planet of plant materials? And I think, you know, I want to acknowledge that there is the potential for that to happen, especially when it comes to timber. You know, when it comes to carbon storage in buildings, the focus is so heavily on timber because that's the plant-based building material we're most familiar with. And that's the one that we actually have to be the most careful with, because it's when we cut down a tree to make a timber, if we weren't making that building out of that product, that tree would remain standing, or hopefully it would remain standing, and it would continue to be a carbon sink, and it would continue to contribute to the forest ecosystem being a carbon sink on the planet. And so in order for timber to be you know, considered as meaningful carbon storage, we have to look not so much at the amount of carbon atoms in a piece of wood, but we have to look and see, is our harvesting of timber from that forest contributing to that forest becoming a larger carbon sink? And if not, then wood shouldn't be part of this equation. But the materials that I'm really interested in that are part of this equation are all the agricultural residues that are generated around the world, all the plant-based fibers that are in our recycling streams. And just as one example, grain straw, which, you know, those of you in Manitoba have definitely seen a field or two of this stuff. There's over 10 tons of grain straw grown already on the planet every year. And that grain straw has already drawn the CO2 of all global transportation emissions out of the atmosphere and into straw on an annual basis. So as we try to create these machines that are going to suck CO2 out of the atmosphere and fix our problem, what we need to do is realize, hey, our farmers are already planting those machines. They're doing their work. All we're doing is by either burning off those residues or letting those residues rot or molder or decompose, we're just sending all that CO2 back to the atmosphere. Whereas if we bundle it up and put it in buildings, you know, we would literally be taking all the carbon from all our transportation emissions and putting it into our buildings. And so that amount of grain straw, I did some, you know, quick back of the envelope math, but that amount of just grain straw, so we're not even addressing all of the agricultural residues that are out there. This isn't sunflower stalks or corn or sugarcane or palm or any of those things. This is just wheat, oats, barley, and rye straws. You could replace every insulation material on the planet and still leave the 20% that most farmers want to turn back into their fields on an annual basis. So we've got lots of it. You can see from this slide that there are lots of ways that people are taking this particular material and turning it into really viable building materials. And, I think if we're going to take our responsibility to the climate seriously in the building industry, our job is to figure out how to smartly get good plant material into our buildings. And that's the challenge. And there are lots of people out there meeting that challenge, as you can see by some of these examples here. Sorry, my screen seems to have frozen. I'm actually going to skip this slide for time's sake. I just quickly want to show you now a case study building, just because I showed you a study, and it's easy to sometimes do things in theory but not in practice. So this is a look at one of our buildings from the Endeavour Center, one of the projects we build with our students. And this is a building where we set out to have some carbon storage, net carbon storage in the building, as well as making it a net zero energy building and having no toxins or no waste. And so we prefabricated this building. One of the interesting things about this building is we wanted to address carbon storage in buildings, not just by stuffing a bunch of carbon into this building once, but we wanted to make it in a way that that carbon was most easily reusable at the end of its life. And for us, that meant making this building as a series of prefabricated components that can go together and come apart and go together and come apart. Because most of our building stock ends up being scrapped, not because it's met its like useful lifespan, like it can't go on being a building, but because the demands for the land or the building change, and we end up tearing down the building to make room for something else. So we wanted to make a building that if it no longer wanted to be where it was or was needed where it was, it could be taken apart and either rebuilt as is, or the components could be used to rebuild something else. And in that way, we can give the carbon stored in the components multiple lifespans. So we actually built this building in Peterborough, took it down, put it up at a design show in Toronto, took it down, and then put it up for a client a little further north in Ontario. So, we were able to sort of prove out that's a thing that we could do. So essentially we made glorified wooden boxes. Some of them we filled with common insulations like cellulose. Some of them we filled with less common insulations like straw, like mycofoam, which is a mycelium-based insulation. But essentially, we made a whole bunch of prefabricated components that come to site already insulated, already sheathed, already strapped, and already with their weather and air and vapor barriers in place, which means that it takes us about 8 hours to assemble this building, floor, walls, roof, and with the exception of big sliding windows and doors, all the windows are already part of the panel when it ships. So you have a closed-in building very quickly. Then we looked at how can we think the same way with our finishes. So in this case, we did not use plant-based finishes. Here we're using steel siding and steel roofing, but we're using it because when we looked at the options, this was the one that you could also take off and put on and take off and put on a number of times, or also take off and reuse in a different way, and you're not actually scrapping the material or ruining the material to do that. We addressed the inside in the same way. So we used a pre-finished plywood as the interior sheathing for the same reason. We're able to use really attractive surface mounted fasteners and then be able to take this paneling on and off, on and off. You can reuse it in this format or take it to other buildings, but now its lifespan has been extended. And we did the whole project, the whole construction here in Peterborough, with only these 3 bags of garbage going to the landfill. So that's 20 pounds of landfill waste. The average building this size puts about 5,000 pounds in the landfill. So we're extremely proud of that. And we managed to make a building that, despite things like steel siding and fiberglass windows and any number of components that aren't carbon storing, the net carbon storage was 25 tons in this little building. And if we'd used a more conventional material palette, it would have had 45 tons of emissions. So we were really proud of the whole project, the approach, and the carbon results here. And what I sort of really am proud of and would like to point out, because you're all building professionals, is that we hit all of these targets with student builders from a small building school where we have a $0 R&D budget. We built a zero cost flying factory, and we made the whole thing code compliant in 3 different jurisdictions. So, you know, this is achievable. And what that means is that people who are smarter and better than us at these things, like you, could, you know, easily do this, or, you know, even do better. So I think our whole industry is capable of, you know, being really innovative and forward thinking, and achieving really great things if we put our minds to it. And I'll just wrap up. I want to sort of introduce the notion of our building emissions calculator, our material emissions calculator at Builders for Climate Action. This is going to be online for our members by the end of this year. And essentially, it's a really straightforward way of being able to look at emissions from materials in a residential building. We essentially ask you to put in the basic parameters of your building design, so the overall sizes and volumes of that building. So you put those dimensions into the calculator, and what you get back is for every component of the building. So if you're looking at foundation walls and insulation and framing and roofing and flooring and sort of all the key enclosure component materials, you're going to get a real-time comparison of what the carbon footprint of all of these options are. So if we have all of these ways of potentially building the foundation for this building, here is the carbon footprint of all of those ways. And so, you know, that allows you to knowingly start making choices. And as you start to choose your materials here, the totals of each material go to a running total, and then you can see the total carbon footprint of your building. And then we have various ways that you can view that, and you can sort of see, you know, where are your big carbon footprints, and then go back and see ways that you could try to reduce those. So I'll wrap up just by saying that I think, you know, even though it might not be the next step in your path to, you know, jump to making, you know, really high carbon storage buildings right away, I think that there's you can set yourself up a very logical and stepped path to get there. First of all, by just stopping doing the very worst things. So making your building out of better materials, understanding what the carbon footprint of those materials is, getting involved in doing those calculations, making your building energy efficient. You know, there's no reason for anybody to be making that red typology building anymore. Like tomorrow, everybody can switch to the blue. There's very little in the way of everybody getting to that yellow, to essentially a zero carbon building pretty quickly. And yep, the green type building with lots of carbon storage is going to take a bit longer, but it's you know, it's going to be something that if you put your mind to it and sort of set up a 5 to 10 year plan, you would be able to move along this progression and do it in a way that's sort of cost effective and works with your business model, and you know, doesn't throw everything into chaos, but that, you know, within a decade gets us to the point where, you know, we are no longer one of the industries that are the main drivers of climate change, but we're actually, you know, doing a significant role in starting to reverse it. So I will gladly take whatever time we have left, and take any questions that people have. I'll go to the chat here, and I can see one question is what high SCM concrete is. So SCM is supplementary cementitious materials. So those are additives that go into a concrete mix that displace some of the virgin Portland cement. So depending on where you live, that might be fly ash, it might be slag, it might be calcined clay. There's some recycled glass SCMs. There's a whole sort of, you know, subset of supplementary cementitious materials that you can put into your concrete. It typically doesn't drive a price change. In fact, the SCMs are usually cheaper. So it doesn't cost more to use a high SCM cement or a high SCM concrete, but the carbon footprint of that is much lower for the same volume of concrete. Okay, I'm seeing a question here about FSC wood counting as less carbon. That's a you know, I briefly touched on the thorniness of wood and carbon storage. FSC and other certifications, the SFI certification, CSA certifications, essentially you're looking for wood that comes from a forest where the wood harvest is not reducing that forest's capacity to continue being a carbon sink. So, obviously if you're clear cutting vast amounts of forest, the fact that you've stuck some of that carbon into your building, but you've ruined a massive carbon sink that would be drawing CO2 to the atmosphere for decades or centuries, those two things don't balance out. So really with wood, you want to make sure that the wood you're using isn't contributing to climate change at the forest level. So it's not enough to sort of count the number of carbons, atoms of carbon in your 2x4 if your 2x4 has, contributed to massive land change use and climate impacts at the forest level. Let's see, next question. The difference between a net zero ready and a net zero carbon building. So this gets to the way, and it's something that we've done in the building industry. We've used energy as our metric for a very long time. We've talked about energy efficiency, we've talked about net zero energy buildings, but carbon emissions or greenhouse gas emissions and energy are not the same thing. So a building that uses, say, 100 kilowatts of roof mounted solar power, it might be using the same 100 kilowatts as a building using coal-fired electricity. So it's the same energy, but the carbon footprint of those two energy sources is very different. So the difference between a net zero energy building and a net zero carbon building is that you're accounting for the emissions associated with that energy. So as you saw in this presentation, the same amount of energy went to heat both of those example buildings I showed, but if it's coming from natural gas or coming from Ontario's electricity, the carbon impact is really different, even though the energy number is the same. Seeing a question about cost, which comes up a lot. The cost for each model ended up being very, very similar because some of those materials, sometimes the high carbon material is more expensive, sometimes the low carbon material is more expensive. It's really a matter of mixing and matching. So for example, on the cladding side, brick cladding, cement brick cladding is the highest carbon footprint and it's also the most expensive. On the other end, when you're looking at insulation, cellulose tends to be the cheapest insulation per cubic foot, and it's also at the carbon positive side of the graph. And so really, you can't generalize. Like it's not like the low carbon building is either more expensive or cheaper. What I tell people is the difference between all of those models was smaller than the cost difference between a sort of normal countertop and a really high-end countertop. That $5,000 to $10,000 that people tend to splurge at, on finishes, buys you, the best carbon building possible. So it's not the cost factor isn't really what's in the way right now. Do you or other building organizations know about have plans to reduce the carbon footprint of existing buildings? Well, with existing buildings, on the material side that I've been talking about, there's nothing we can do, right? Those materials have already been made. They're in the building. Those emissions went in the atmosphere back when that building was built. So there's nothing we can sort of do to address that now. We can make the building more energy efficient and I should use my own terminology, more carbon efficient on its operations. And that would be the biggest thing we could do. But it's important to remember with building renovations and upgrades, the same thing applies. If you blast a building full of a really high emitting insulation, an existing building, hoping to reduce its operational carbon footprint, you may have, in using that high emission insulation, made a carbon impact that the operational side will never pay back. And because with renovations, we're often getting less energy efficiency than we can by addressing it at the new building state. It's pretty easy to improve the energy efficiency of a brand new building by 50%. but on a major renovation, especially of a larger building, an improvement of 25% is amazing, and that's good. We should be doing that, but it just means that the margin is even smaller. So if we expend a whole ton of spray foam insulation trying to make an existing building 25% more efficient, we may never actually see that as a total climate benefit. Have we been monitoring the performance of the panels? Yes, we do. I spent the first 10 years of my career putting monitors in every possible place in every wall and attic that I built. And to be honest, like, there wasn't a single issue anywhere. We've got 50 odd buildings under our belt between my former private practice and Endeavor Center, and there hasn't been any material failures, any moisture issues, any mold, any insects, any of those things that people sort of automatically assume are going to come with biogenic materials, just has not been the case. And I think as an industry, we need to trust ourselves to be smart enough and talented enough to be able to do this with these kinds of materials. We've actually been building wood frame buildings for a long time. If you are confident that you can build a wood frame building that is going to last a good long time, 100 years or more, the other biogenic materials you're going to put in that building have the same properties as the wood. They're no more or less prone to damage from the same things that the wood would be damaged by. So if you feel like your practice is at the point where you can build wood frame, then you can also build with all of these other materials. Question from Cindy about agricultural waste and not composting it back into the soil. I tried to address that. Most, especially with straw and hemp, that material does not break down into the soil very well. All the farmers that I've talked to and all the papers I read on it said that 10 to 20% of that material being turned back into the soil on an annual basis is all that the soil can handle. And so that means that there's potentially 80% of that left to be used in other ways, such as making building products. And again, a quick back of the envelope calculation on the amount of grain straw we grow in Canada and the amount of houses we build is we could switch all our insulation to straw-based insulation in Canada and use less than 50% of each year's straw harvest. So, and that's not even talking about the hemp harvest or the sunflower harvest or other possible streams for those ag materials too, or things that come out of the recycling like paper and cardboard and things like that are already used to make cellulose insulation. So I think that the pool of those materials that's already being generated far exceeds what we would be tapping into them, even if we did tap into them at the widest possible scale. Well, I guess I'm just a minute or two over time, and also it looks like I'm at the end of the question list. So I think I packed a lot into a short time. I hope that wasn't too overwhelming, but I really want to thank everybody and for the opportunity to be able to talk to you, and thank you for the really great questions and your attention for the last hour. And you're on mute, Laura, if you're trying to talk to everybody.
Classic. Well, thanks so much, Chris, for the time that you took today to speak to us. That was really informative. I loved seeing all the questions in the chat. Yeah. And hopefully we can apply some of this information going forward. So yeah, have a great day, everybody. Be safe out there. Wear your masks. Try and stay social distance from people. It's a tough time in Manitoba, but we'll build our way through it. Okay, so thanks again, and we'll see you next time later in November for our next Lunch and Learn. Stay tuned for more information on that.